going to talk about words and concepts, particularly in the context of analogy. So this very conceptually productive kind of logical idea. This is really going to be an outline of a proposal of a way towards using classic word counting techniques for building distributional semantic spaces and moving from there towards more geometric approaches to things like analogy. I'll be covering first an overview of an ostensibly geometric method that is already existent in the literature for solving analogies. And I'm going to cover a couple problems with that method as well. Then I'm going to introduce a novel distributional semantic model that dynamically projects new conceptual spaces based on an analysis of a certain context, so something going on in the world. And finally, I'm going to propose a new methodology based on this dynamic approach to distributional semantics, and offer a couple ideas about how we can really use the geometry of these spaces to do some productive conceptual work. But my disclaimer is this is very much a work in progress, so rather than a result, I'll be offering you a kind of a proof of concept, and we'll see what everybody thinks of that. But to begin, McGregor et al., these guys who work at Google, have produced this very interesting result. They've used a deep neural network to an RNN to build a distributional semantic space where it turns out this very interesting linear algebraic property exists. You can do some basic math to figure out that dogs are to cats as puppies are to kittens. And this is really quite a remarkable property of this space. It wasn't built to do this. This just kind of works out in the geometry of this space. So you can imagine that sitting somewhere on the surface of this hypersphere, of this normalized space of word vectors that these guys built, is a shape that looks kind of like this, a parallelogram. And this approach has been pretty effective. These results I actually got using the word vectors that McGregor and friends have released to the world. The corpus itself is, I think, proprietary, so it's hard to do any more experiments on that. But anyway, it tells us things like France is to Paris as Finland is to Helsinki. Girls are to boys as princes are to princesses. Fast is to faster, as big is to bigger. Pretty good. This all makes sense intuitively, but it really only works to a point. We have elephants are to mice as big is to huge. Bank is to river as shoulder is to elbow. And picture is to paint as story is to Mexican Viagra. So, you know, we can kind of begin to guess the types of spaces where this will work and the types where it won't, or the types of analogies that play out the way we expect them to in this space. In this case, the model is missing something about the relativism of elephants and mice in terms of the domain of, or the dimension of size. In this case, clearly the system is getting tripped up on the ambiguity of shoulder, and I don't know exactly what's going on down here, but it's definitely missed something that's maybe slightly metaphoric about whatever we do expect that last word to be. So I mean, and this kind of makes sense, because in a space generated by a neural network, or for that matter, another type of distributional semantic space where we apply something like SVD to the space to get a more efficient and dense space, the dimensions are by design maximally informative. But what this means is that we can't capture any of the contextual stuff that's going on in these examples. We can't figure out that this is the context of relative sizes, or the context where we're talking about shoulders and roads, not shoulders as body parts. So what we propose is that we can use a very sparse, big, so to speak, very high-dimensional distributional semantic space where we keep literal, what I'll call literal co-occurrence values, so co-occurrence values that tell us something statistically literal about the corpus from which we derive the word vectors. And in this kind of space, we should be able to begin to project contextually subspaces where we can figure out why banks are to rivers as shoulders are to roads. So we begin by building a space like this. We use a fairly typical PMI type metric. We keep everything positive. It's not exactly PPMI, but it's something like that. And as you would expect, we built this space just based on English language Wikipedia. And you get a space where words are close to other words that have some sort of semantic relationship to them. But as you would also expect, this space is messy. We have a few different kind of senses, or at least interpretations contextually of cat here. Are cats beasts in jungles, or are they cute little pets in houses? Well, our idea is that we should be able to basically take perspectives on this type of space and discover that from this point of view, cats have to do with lions and tigers in jungles. Whereas from this point of view, cats have to do with dogs and hamsters in houses. And the way that we do this is we basically analyze our input terms. So we choose the, we take a look, so we're turning to the example where word2vec really failed. We take the dimensions, or, where if we're trying to analyze this space where this analogy works out, where the fourth term is the one we're looking for, we take the dimensions where these PMI values have the highest mean value for the three word vectors that we're looking at. So basically we're beginning to think about how do we solve this analogy, A is to B as C is to D. Well, we start by looking at A, B, and C. And in order to kind of test the model, or in order to offer a proof of concept, we've held back 1,000 analogies from that same data set that Nicola et al. Used. And for each of these 1,000 analogies, we've picked the 200-dimensional subspace that satisfies this property for A, B, and C. So we choose, for picture, paint, and story, it turns out that tone, relate, and gray are all dimensions where there are relatively high PMI values for all three word vectors. And there was a fourth one here I forgot to label, sorry about that. And then what we're going to do once we've selected this 200-dimensional subspace is we're going to choose the 20 dimensions in that subspace, so a kind of subspace where the relationship A minus B equals C minus D is most closely fulfilled. And what we get, I'm sorry you can't read the words here, but in a way that's actually good, because I want to emphasize that I don't want to spend too much time interpreting what the labels of these dimensions mean. But what we get is a space of dimensions that look kind of like this. In terms of whether or not this works, out of the 1,000 analogies that we held back, 3 analogies contained words where either the A, B, or C component of the analogy wasn't in our vocabulary, so we kind of had to throw those out because we can't say things about words that our model doesn't know. Of the remaining 997, 996 satisfied this equation when we built the spaces in this way. And when we begin to look at the dimensions that work for these kinds of subspaces, so when we begin to look at the dimensions where these analogies work out as the kind of geometrical arrangements that we expect or that we want, we notice something kind of predictable but also kind of interesting about the way the words are kind of clustered along these dimensions. So here, for instance, we see story and picture are quite close to each other. By the way, this is just basically a histogram. So what we have is PMI value here, and then this just ranks every word vector that has a non-zero value for this dimension, which in this case is the dimension labeled tone. And we rank I guess there's about 2,000 of those, 2,000 non-zero word vectors for tone. What we notice is in terms of the y dimension, which is what we care about, the PMI value, these word pairs begin to cluster in interesting ways. So here we have story and picture, and what we've decided word is the answer to this analogy, which is maybe controversial. But these cluster here. Likewise, here paint and picture group together, and word and story group together. And then here word and story group together down here at the bottom of the histogram, and picture and paint group together up here. If we imagine kind of extrapolating this type of relationship across about 20 different dimensions, we end up with a geometry in our analogical subspace that looks kind of like this. We begin to get a situation where the parallelogram described by the points of our analogy that we're trying to map gets pushed out into a very central part of the positive region of our space. I mean, everything's in the positive region, but it also tends to be at roughly a perpendicular angle to a center line extending directly out of the origin. So what I'll leave you with is this, that I think that we begin to see that there's something interesting about the geometry of the way these words sit in this space that we can use to begin to look for the kind of context where these analogies work out. And the key thing here really is that these subspaces, what they represent isn't just a bunch of words that happen to co-occur in interesting ways with these words. I'd like to think that we can begin to talk about these subspaces as being themselves a context, something based on a situation in the world, And if we can understand how to define those contexts, then we can begin to do some interesting mathematical stuff with these spaces. For instance, we might expect that if we kind of skewed the transformation skewing away from the origin, the eigenvectors in this space would be the lines connecting the words that work out in an analogical relationship. So that's it from me. I mentioned Mikolov's work, but there are the other people I know of who are doing kind of similar work projecting contextual subspaces from distributional semantic spaces are Laura, who's here today, and these guys who I don't think are here today. I've never met them, but there's also other work beginning to happen in this direction. Thank you.
This is really interesting work. A quick question about the 996 hits. So when you say that they satisfied B minus A plus C, is approximately D, is that like, is that nearest neighbor or 10?
No, it's the nearest neighbor.
It's the absolute nearest neighbor.
Yeah,
Okay.
but I mean now, just to be absolutely clear, we're kind of cheating here. We're using information from D, so we haven't solved the Google analogy test.
Right.
But I think we've at least we know a direction where we can start to look at the way to define the subspaces where we do expect to be able to solve that quite consistently. But yes, it's a nearest neighbor, so we use basically this exact same approach that these guys used. And if it's not the nearest neighbor, then you failed to solve the analogy.
This is really interesting, and you said it was a proof of concept, and I'm just wondering what would be the next step in this, and what would be the best results you could achieve if you extend this method?
Well, I think there's a few different ways to go. I mean, for me, the interesting thing next will be to begin to really look at the geometry of these spaces and think about ways that we can exploit that. So for instance, on the one hand, do we want to just try and solve that test set? That would be interesting. Can we know things about these 3 points, being completely unaware of what that is, and still begin to guess the dimensions that would put what's now kind of a triangle in the orientation where we're expecting to be able to complete the other half of that triangle in an interesting way. But on the other hand, maybe we could do things where we take all 4 of these terms, we build this subspace, and then we look at their relationship to other kind of shapes. Could we capture metaphor, for instance, by finding other region is the wrong term here, but other arrangements of word vectors in this space that also behave similarly under a transformation, and then say that, well, now we have a metaphor. So could we have a shape of, say, butchers, a shape of surgeons? Maybe the butchers has butchers and cleavers and carcasses and stuff, and project one into the other and discover, we now have a space where this metaphor that surgeon was a butcher works, or makes sense.
So how many dimensions in your vector space?
So in the base space, there are about 7.5 million. We keep everything, basically every word type in Wikipedia is a candidate dimension.
So you don't lemmatise?
No, we don't limit. We haven't lemmatized, but that's one. There are a lot of parameters in these types of spaces, as you know, that we could play with, and lemmatization would definitely be one. Part of speech tagging could be interesting to kind of. This model is supposed to be good at disambiguation anyway. So actually, hopefully, you kind of get past the need for part of speech tagging to a certain extent. But that could help. Any new information is good information.
And then you take subspaces of this space to be conceptual spaces?
I don't know if I would want to quite make that strong of a claim. They're moving toward, in the long run, again, to address what's happening in the future, it would be great if we can get spaces that kind of work out as what you might call ad hoc taxonomies, where we can think of directions as being these semantically loaded relationships between words. But I would be a little bit nervous to actually call it a conceptual space, because we don't really know much yet about how to interpret the dimensions. That's definitely the direction we're moving, and can we do that? Can we get spaces where we can really interpret? I don't think we'll ever be able to interpret these literal co-occurrence dimensions. I think that's a mistake. But can we interpret directions within these spaces in the way that the theory of conceptual spaces suggests we would want to?
But you would call them semantic spaces?
I would call these still lexical spaces.
Lexical
Or
space.
semantic spaces, I don't know, I won't split hairs about it, but yeah, semantic space. They're still in the realm, that kind of low level connectionist realm of, you know, the word meaning relationships, but hopefully moving up towards the geometry of concepts.
So it's one of the suggestions of what you might do for the take us to the next level. The one thing that's been a bit of a holy grail in, or at least a sort of undiscovered thing that we want in this space for a long time. It was mentioned earlier that one of the standard objections or criticisms of kind of semantic space models is that opposites end up close together, which they do in natural language. Hot and cold are often mentioned together. I just mentioned them together. It's very, very normal. And the suggestion that's been around for quite a long time, but I don't think anyone's ever pulled off, I might be wrong by now, is that, well, hot and cold are very close together in the space, but if you find the right subspace, they would be opposites within the context of that subspace. So if you can find subspaces that then give you opposites, then that would be big.
Yeah, that would be great. I mean, since this is the way we've constructed this model, everything is in a positive region of the space, so I don't know exactly how opposite would be defined. I mean, at the origin in one of these subspaces basically means nothing. It's not in the subspace. This is not an interesting space for whatever that word at the origin is. But absolutely, I mean, negation is a really tricky one, and yeah, maybe I don't know what the way would be, but it would be great if there were a way to reflect oppositeness in an actual opposite spatial way.
Let's try later.
Right, we need to stop there. Thanks, Dan.